Welcome, everybody, to another one of our Friday discovery sessions. Happy Friday to everybody. We made it through another week. I know if you are joining from Ottawa, it was a really, really cold one. So we survived. We made it through. Congratulations to everybody for that one. I am Kirstin. I'm the community organizer with Efficiency Canada. And as I said, I'm joining from Ottawa, which is on the traditional and unceded territories of the Algonquin Nation. You may also be able to tell that I am not Natalie Irwin. So Natalie is off to some really fantastic new opportunities with the Office of Energy Efficiency. We're definitely sad to see her go, but also really, really excited about that great opportunity and everything that's coming next for her. So congratulations to Natalie. What that also means is that we are hiring a new director of engagement. So that's a great opportunity to continue Natalie's really impressive legacy of bringing the sector together and building a community for change. So I will put a link in the chat with a few more details about that if that sounds like an opportunity you would be interested in. As with all of our discovery sessions, so we are going to see a presentation for about 25 minutes, and the rest of the time will be for questions. Throughout the call, if you have a question that pops into your head, your Q&A button is at the bottom of your screen, so feel free to drop your questions in there, and we'll get to all of them at the end of the presentation. During the Q&A period, you're also welcome to raise your virtual hand, and I can unmute you to ask your questions directly. With that, I am excited to welcome Anthony Pack, the principal of Priopta and CLF Vancouver. Anthony is going to start to answer one of the big questions in the building industry right now. How can we better understand and reduce embodied carbon? So with that, Anthony, you can take it away.
Thanks for inviting me for this presentation, and thanks everyone for your interest in this topic. So I'm going to be talking about embodied carbon, which I oftentimes refer to as the blind spot of the building industry. Just a note, I'll be representing the Carbon Leadership Forum. If you're not familiar, the Carbon Leadership Forum is a great hub of activity around embodied carbon, and we actually have these local hubs all around the world. I started out the Vancouver hub, but we have hubs in Seattle, in Alberta, in Toronto, in Ottawa. So definitely encourage you to get involved with the local hub if there is one in your region, and if there's not, you're welcome to start one as well. Okay, so today I'm going to be talking about why embodied carbon matters, how embodied carbon compares to operational carbon, which is a topic that obviously many of you are probably very familiar with. And then I'm going to go into some specific strategies for how we can reduce embodied carbon from some of the key materials, things like concrete, wood, steel, and insulation. So first off, why does it matter? When we're talking about embodied carbon, we're referring to the emissions associated with the construction materials. So think of all the materials that go into a building. All of the concrete, steel, glass, wood, insulation, etc. All of those materials have emissions associated with it. And we're looking at emissions across the life cycle. So everything from resource extraction, manufacturing, processing, transportation, all the way to end of life, deconstruction, demolition, landfilling, incineration, recycling, etc. So we're looking at all those steps throughout the life cycle of all the materials that are inside of a building, and we quantify all of the emissions associated with that. Now, how significant are these emissions? If you actually look at the global annual CO2 emissions, you'll see that about 28% of global CO2 emissions is associated with operational carbon emissions. So that's all the emissions associated with heating and cooling and operating all of the buildings on the planet, 28%. A further 11% is associated with the embodied carbon. So that's all the new construction and major renovation that takes place each year. So all the materials that go into that, that's about 11% of global emissions. What's interesting is if you divide up the pie in different ways, if you just look at even three of the key materials, concrete, steel, and aluminum, together they make up about 22.7, almost 23% of global CO2 emissions. Now, the reason why this is much bigger is obviously these materials get used not only for buildings, but it also gets used for infrastructure, for in the case of steel and aluminum, things like cars and other products, right? And so if we can influence the embodied carbon of these supply chains of some of these key construction materials, it'll have an impact not only in the construction sector, but more broadly as well across other end uses. So this is actually a really cool graph that I recently found. And so I'm going to take you through a little bit of a tour of this. This is actually a global flow, a picture, a Sankey diagram of the embodied carbon emissions associated with, well, the entire world's emissions, essentially. So you can see, the entire world's emissions, about 59 megatons of CO2 equivalent. And so from the left side, it's the resources, so fossil fuels, minerals, ores, biomass, waste, and then it moves through all the different steps. So the way to read this is like for each column, essentially the width of these, if you add it all up, it's about 100% of the emissions. And so as you go from the resources all the way to the end use, so how much of it makes its way into mobility or transportation, housing, communication, healthcare, services, etc. Those are the end uses. Now, I know this graph is probably a bit hard to see, so I'm just going to zoom into some of the key areas. So if you zoom into just this certain section of the diagram, right here, you see some materials here: sand, clay, stone, metal, ores, wood, etc. And those emissions seem kind of small. But then as you move towards this section where you see cement, iron, chemicals, plastics, rubbers, wood products, other materials, you see it actually grows quite a bit, because there's emissions not only just from the extraction of these materials, et cetera, but there's also a lot of energy that goes into these materials. And so that's one of the cool things about this diagram is you can actually see the flow of energy into these products. And so this makes up a significant slice of emissions here. And then you can see how much of that makes its way into construction materials and manufacturing. So for example, with manufacturing, then some of those go into vehicles, electronics, machinery, and whatnot. But for what we're looking at today, it's mainly in the construction materials. So these construction materials, how does that make its way into our buildings? So if you look on the left side, this is residential buildings. This is non-residential buildings. So these are all the buildings altogether. Now, a lot of the emissions come from the energy use. So that's this slice. This is the energy efficiency, the operational carbon emissions. Same thing on the non-residential buildings. You see this flow right here. But then you can see where the embodied carbon, the materials, come into play. So how much of that makes its way to residential buildings and non-residential buildings. So very significant slice of the emissions. And this has been a blind spot because we have not been quantifying these emissions for most of our new construction projects. So let's get down to the building scale. How does this compare with operational carbon emissions? So the metric I want to look at is kilogram of CO2 equivalent per meter squared of floor area. So when you look at a typical building, let's say it lasts for 60 years, the yellow bars, obviously each year there's certain emissions associated with operating the building. So heating and cooling and operating the building. That's the yellow portion, that's the operational carbon emissions. And during the design phase, we quantify that using energy modeling. Now, the red bars represent embodied carbon. So there's a big pulse of emissions up front when you first construct the building. That's all the materials that make its way into the structure and envelope and all the other components of the building. And then throughout the lifespan of the building, we'll include things like replacements. So certain components, if it doesn't last for 60 years or the lifespan of the building, there's obviously replacements. And so we account for that. And then at the end of life, when we deconstruct the building and those emissions go to landfill or recycling or whatnot, we quantify emissions there too. So that's during the design phase, we quantify that through life cycle assessment. And when we do a life cycle assessment, we actually look at multiple environmental impact categories. The one that most people are concerned about is global warming potential, which we refer to as embodied carbon. But just know that there's also other impact categories we're looking at, like acidification potential, eutrophication, smog formation, depletion of non-renewable energy, and ozone depletion. And so I mentioned we quantify this using life cycle assessment. What do we mean by life cycle? Well, there's actually formal definitions for each of these life cycle stages. So for example, we have what we call module A, B, C, and sometimes we report D. But A to C is kind of the cradle to grave, so to speak. So module A is the upfront carbon. So that's everything including raw material supply, so extraction, transportation, and manufacturing. So the emissions that, let's say, sometimes you may see environmental product declarations from manufacturers, they're mostly reporting the emissions at these stages. So basically everything up until it leaves the manufacturing facility. And then we get to A4, which is transportation to the construction site, and then A5, which is construction installation. So all the A stages combined, this is basically before the building is occupied, all the emissions up until that point. Then module B is the use phase. So that's the biggest portion is probably the replacements. So when we have replacements, we'll account for that, but we also include things like maintenance, repair, refurbishment. And then module C is the end of life emissions. So typically you see LCA studies reporting A to C. Sometimes they may report module D, things like reuse, recovery, recycling. This is benefits and loads beyond the building life cycle. So basically, if you recycle materials, for example, that's going to impact the next product's lifespan or whatever that recycled material goes into. And so in a way, you're trying to quantify those benefits, but it's a little bit out of your system boundary. Now, this A to C, this is the embodied carbon. But if you factor in operational energy use, so that's like operating the building, that's the energy modeling results, for example, or your utility bills once you actually are in operation, you add those two together, that's how you get the whole life carbon, the holistic picture of the carbon emissions of your project. Now, historically, the thinking has been that operational carbon emissions are far more significant than embodied carbon. And so, we don't even need to look at embodied carbon because operational carbon emissions is where most of it's at. Now, I don't want to paint this as like pitting one versus the other. We need to address both. But in certain regions and over time, certain places, as we decarbonized our buildings and started to get cleaner electricity grids, have more renewables in there, and design more energy efficient buildings, this operational carbon is decreasing. And so embodied carbon becomes a bigger slice of a smaller pie, so to speak. So let's start off with operational carbon emissions. These are numbers that maybe you're more familiar with, but let's say a baseline building in Vancouver, maybe that's around 20 kilograms of CO2 equivalent per meter squared per year. Whereas a place like Calgary with a lot more fossil fuels, a lot of natural gas heating, colder climate, and also higher carbon intensity in their electricity grid, it can be as high as 71. So it can kind of vary a lot. This is kind of a baseline building. Now, in BC, we have the BC Energy Step Code. And so this was a study done by Integral where they looked at across the different steps. As you get higher in the steps, you get more energy efficient. But there's also variations between mechanical systems. So if you have electric driven systems like heat pumps and baseboards, you can actually get the emissions very low in BC because we have a lot of hydroelectricity and the electricity grid is relatively low carbon. And so as we drive the operational carbon numbers down quite a bit, embodied carbon becomes a bigger slice of that. So that's the operational piece. What about embodied? So these are two different sets of benchmarks that look at roughly over 1,000 buildings. In the Carbon Leadership Forum back in 2017, they created this study where they looked at the range, and you can see generally the results are, let's say, between 100 to or below 100 to a little, sometimes over 1,000 kilograms of CO2 per meter squared, with many of them in the, let's say, the 200 to 600 range. Similarly, in One Click LC, which is one of the software tools, they've created these benchmarks. And so they can kind of show you what's the median or the D level, and then what's considered good, what's considered high emitting. And they show you ranges across all of these. And so these are just kind of examples of just the rough order of magnitude that you can expect for some of these projects. So when you piece those two together, when I mentioned in the BC example, this is actually one of our current projects. You can see like the embodied carbon is about 558 kilograms of CO2 per meter squared. But then we compare that with the operational carbon emissions over 60 years. And it depends on what you're comparing against, obviously, because we're in the design phase. So with our energy modeling results, we can see right now, even over 6 years, because this is the operational carbon emissions have come down so much, it's 90% versus 10%. However, if we compare it against the typical office building, this is based on actual measured performance, that brings it to, even then, it's still about 40% after 60 years, right? And it's important to note with embodied carbon, these emissions are mostly upfront. So these emissions have already happened, whereas operational carbon emissions could potentially go down over time as we clean up our grids, for example. There's big differences in our electricity grids. So we have BC is very low, Ontario is very low. This is grams of CO2 equivalent per kilowatt hour. So you can see there's big differences between our grid versus grids like in Alberta or in Saskatchewan, which are much higher, right? And that's going to affect your operational carbon emissions, but it also affects embodied carbon. If your products are produced and they use a lot of electricity, it matters what the source of electricity generation is. So there's many policies and certifications that are looking at this. I won't get too in depth in this, but the city of Vancouver is taking a lot of action on this. Soon we're going to be requiring reductions in embodied carbon for some of the rezoning projects. Currently, we need to disclose, and we need to do LCAs to just disclose these results to the city, but soon we're going to move into reductions, and that's in line with the city's climate emergency action plan, which states that by 2030, the embodied carbon of new construction or new buildings will be reduced by 40% relative to 2018 as a baseline, and that's going to apply across the board to all projects. So it won't be a voluntary requirement. There's a lot of regulation coming into play, and Vancouver is definitely a leader in that sense. And there's also some of these other certifications, the kind of voluntary standards, things like LEED, Canadian CGPC Zero Carbon Building Standard, ILFI's standards. They all have address embodied carbon in certain ways and reward reductions. Okay, so now I'm going to get into some of the strategies for how you reduce embodied carbon. So for example, with concrete, this oftentimes is one of the most significant materials from an embodied carbon perspective. So what can you do? First, the low-hanging fruit is to push for using Portland limestone cement instead of regular Portland cement, or GUL versus GU. So the typical regular Portland cement, if you replace it with this GUL, Portland limestone cement, that roughly leads to about a 10% reduction in the global warming potential per meter cubed of concrete. And generally, there's not too much of a performance hit or even a cost premium per se associated with this. So this is something to push for on your projects. Next is looking at reducing the cement content. So most of the emissions associated with concrete comes from cement. And so if you can reduce the amount of cement used and replace it with supplementary cementitious materials, so that's things like fly ash or slag, that can reduce the cement content and then reduce the emissions overall of the concrete. And some design parameters that you could do is, for example, for certain elements, well, actually, you want to optimize the concrete mixes across each building element. So, maybe for your foundation, you can have higher SCM content, whereas maybe the suspended slabs, you can't go as high based on curing times and the construction schedule, because this can affect the construction schedule as well. So, but you want to really look closely, work with your structural engineer on each of these elements and how do you optimize your concrete mixes across all of them. And where possible, if you can move to 56-day curing time versus 28-day, that can give the ready mix supplier more room to actually lower the embodied carbon of the mixes that they're producing. And then also moving towards performance-based specifications and avoiding prescriptive specifications. So for example, prescriptive specifications where sometimes you might be specifying the minimum cement content, maximum water to cement ratio, maximum SCM, et cetera. Those things can limit what a supplier can do in terms of the embodied carbon of the mix that they deliver. But if you instead just move towards performance-based specifications, that gives them more room to lower the carbon intensity of their mixes. So just to give you an example, this is from the industry average data from the Canadian Ready Mix Concrete Association. If you compare against the benchmark, per meter cubed of concrete, if you use GUL, the Portland limestone cement, and you increase the SCM content, you can get up to 40% reduction. And then some of the local ready mix producers that have started producing their own environmental product declarations are getting close to like 50% or even beyond 50% reductions on some of these mixes. So there's a lot that you can do with concrete. It's not that like all concrete is bad, but there's a lot of room to improve. Next up is wood. So you've probably heard a lot of talk about mass timber. Wood generally does come out, or wood framed or mass timber buildings typically do come out with lower embodied carbon compared to other, like concrete or steel framed buildings. However, I just want to note that when you're looking at these numbers, a key thing to understand is whether these studies include biogenic carbon accounting, and in particular, whether they factor in the carbon stored in the wood. I won't get into this topic, but it's a big point of difference sometimes. And more importantly, we need to really look at how our wood products are produced, or what's happening in the forest. How we manage the forest is a huge factor and potentially a big blind spot for us. And that's where a lot of those emissions are oftentimes not factored into they aren't factored into our LCA studies, but those factors can be far more significant. So that's a whole nother topic into itself, but just know that like sustainable managed forest is a big deal. We need to look into that. Yes. Next thing is steel. So just to give you kind of a high level overview, there's two main ways of producing steel: basic oxygen furnace and electric arc furnace. So basic oxygen furnace is how we produce most of the primary steel. It accounts for about 71% of global steel production. It has much less recycled steel content. This is how we kind of produce the primary steel. And it's much more emission intensive, sometimes 2 or 3 times higher emission intensity than electric arc furnace. With electric arc furnace, you're using mostly recycled steel. So that accounts for maybe about just under 30% of global steel production. And it's, as I mentioned, much lower emission intensity. And because it's electric driven, it's an electric driven process, it matters what the carbon intensity of the electricity grid is, where that steel is produced. So generally speaking, I think in Canada, we're about 60% basic oxygen furnace, that's the higher emission variety, and about 43% electric arc furnace. And so on a project level, if you can specify electric arc furnace steel from lower carbon states or provinces that are producing this, that can generally reduce the carbon intensity of your project. However, I should mention that from a global picture, we still need to figure out how to decarbonize primary steel production because there's not enough recycled steel to essentially satisfy global steel demand. And so even on a project basis, if we can reduce emissions by specifying lower carbon steel, we still need to figure out the big picture of like, how do we decarbonize primary steel production? And that's where you sometimes hear about things like hydrogen, using hydrogen for primary steel production. That's a really important piece. Finally, insulation. The take-home message here is I just want to point your attention to 2 forms of insulation in particular that are very high embodied carbon, and which was a bit of a blind spot because it wasn't properly accounted for even in our LCA tools sometimes. And that is XPS and spray foam. And the reason is because they use blowing agents that have very high global warming potential. These blowing agents are historically have been mostly HFCs, hydrofluorocarbons, which are essentially the same as like refrigerants that you use in your mechanical system. So they're very high impact, and small releases of these gases they're like thousands of times more impactful than CO2. So essentially with these blowing agents, they off-gas over time. And so that leads to a lot of emissions. And so if you actually compare against different forms of insulation, so the top part, most of this is like XPS. Oh, actually, no, sorry. Let me go back to the previous slide. So the blue line items that I have here, this is showing different manufacturer-specific EPDs. You can see the impacts are quite high for the blue ones. That's using the HFC blowing agents. But the industry is transitioning towards using HFOs. So that's a much lower global warming potential blowing agent. And that can reduce the emissions quite significantly compared to the previous forms. So until about a year or 2 ago, all the XPS insulation and most of the spray foam in North America use HFC blowing agents. So for example, the typical XPS that you would just buy, much higher impact. And this was very significant even at a building basis because it could significantly increase the emissions associated with that. So right now, as of 2021, we have new regulation in place in Canada. And so manufacturers have had to come up with new products to meet that regulation. There is a bit of a temporary period where there's still some of the old product available and there's exemptions given to certain manufacturers. And so in this interim period, I can see that this old stuff is still being sold. And so this is probably one of the big takeaways on your projects is to look for the lower global warming potential blowing agents. So in your XPS products and also in your spray foam products, because they can reduce your emissions quite significantly. Now, if you look across XPS and spray foam, I also included these gray line items show like different types of other forms of insulation. So things like EPS, polyiso, mineral wool, fiberglass bat, cellulose. These are all quite low and there's differences between them. But if you just look at these yellow bars, the XPS and the spray foam can be quite a bit bigger, quite a bit higher than these other forms if you don't specify the lower carbon intensity ones. And the good news is there are new products coming onto the market right now. But just know that, even though Canada has this new regulation as of 2021, not all these products are like, how do I say it? Some of the old products are still being used in this interim period. And in the US, if you're working on projects in the States, many states don't have regulation around this. And so you have to actively look for this product in certain states. So that's just something to keep in mind. With that, I'm going to open it up to questions. I do want to reiterate, if you're not involved with the Carbon Leadership Forum, I would highly encourage you to sign up and join a local hub. There's also an online forum with lots of active discussions on all things embodied carbon. So please join with that. Here's my contact information if anyone wants to reach out as well. And we'll open up for Q&A.
Awesome. Thank you so much, Anthony. I think I really appreciated seeing those numbers so clearly written out of, what's causing greenhouse gas emissions and what are the different sources and how can we address it. I think that was really useful for our audience. And we've got some great questions here. So the first one here from Robert, and I don't know if you are privy to this information, but if you are, the audience would love to know, to what degree is the upcoming National Model Building Code going to impact the embodied carbon in buildings?
That's a good question. I think I haven't looked at this specifically, but I know up until this point, a lot of these discussions have kind of existed in silos. So like typically embodied carbon's kind of got its own set of policies and modeling efforts, and then operational carbon, energy modeling, et cetera, is a little bit different. And I think we need to do more studies to look at the intersection. So I'm not familiar specifically, but I would imagine there's kind of a different trade-offs in different regions, right? Because you have different operational carbon intensities first off. And so there's a different benefit that you can achieve on it, city to city. And then there's also the embodied carbon piece. And a lot of that comes down to, in particular, the insulation products that are used. And yeah, so it's not even just like one type of insulation versus another type of insulation. It's like different brands of insulations can also have an impact on that.
Awesome. Thank you for that. And I don't want to promise anything that isn't necessarily going to come to fruition, but we do have a blog coming out soon on how we really get to truly zero carbon building codes. And so I think we'll be talking a little bit about that coming shortly. Question here from Brendan. How much of the embodied carbon comes from energy use versus non-energy sources such as chemicals?
That's a good question. I mean, it depends material by material. So in particular, concrete, that's one of the higher emitters, right? I think something like 60% of those emissions are chemical related, or like it's just a function of the actual chemical reaction that takes place in producing the cement, whereas about 40% of that is the energy input into heat the kilns. And so that energy input, yeah, like maybe some of the cement producers are using, I don't know, biomass or whatnot to fuel it. And so there's ways of decarbonizing that piece, but the chemical portion is more challenging on that. But the mix varies depending on material, obviously. But for concrete in particular, that's a very significant one.
Awesome, thank you. And just for some folks putting questions in the chat, I would encourage you to use the Q&A. That's where we draw most of our questions from. So you'll see that at the bottom of your screen. It looks like 2 speech bubbles. So a question here we've got a lot of policy wonks in our audience. So what are the best policy strategies that you can use to use demand side pressure to actually reduce GHGs from upstream production processes or remove some materials from the market? So looking at the policy options here for addressing these issues.
Yeah, we're involved in some of these conversations as well at the provincial level and with the city as well in BC. But so I think the first step is just get to disclosure, right? Require disclosure. That's what the city of Vancouver did. So, and that builds up a lot of industry capacity locally amongst all the consultants, and it gets everybody looking at these numbers. That's the first step. I would say also creating a roadmap for where we're going. So for example, in Vancouver, they're saying, 40% reduction by 2030. And then they create a roadmap. Okay, how are we going to ratchet that up and what does that look like? I think similarly, something like the BC Energy Step Code, that type of a framework, we could apply something similar with embodied carbon, where we have different steps or maybe aligning with the step code, different steps along the way. And so, maybe it's like 10, 20, 40% reduction. Maybe the first step is disclosure. That's a possibility as well. So I think, but having these reduction requirements is really important. And it's important to look at these policies both at a building level. So that's, like looking at all the materials in a building, you got to achieve a certain percentage reduction. That's one strategy. You'll notice in the States, you'll see a lot of buy clean policies. Those are material specific policies. So they're more kind of trying to reduce the emissions of like concrete specifically or steel specifically or certain categories. So I think both sets of policies have a role to play. Yeah, but I would encourage you to think of both sides.
Awesome. Yeah, great answer. And a question here from David. How do you do comparisons like reusing or improving the existing products in existing building with retrofits and comparing that with using a totally new product or totally new equipment?
Yeah, that's a good question. I mean, I think you would need to do let's say on a building, and we're involved with this Pembina Reframed initiative, which so soon we'll be doing some analysis on this as well for a couple retrofit projects. But essentially, you would need to quantify the emissions associated with all those materials in the retrofit. And I think in an ideal scenario, maybe you would then compare it against what it would have taken to, like, if you demolish that and built new, right? And looking at the delta between that, that's probably how you would quantify the impact of that. Yeah, but I think it's definitely an important thing to think through and also have that interaction with the energy modeler or figure out how, like, where's kind of the sweet spot between operational carbon and embodied carbon.
Awesome.
And one more thing also, I didn't mention mechanical, electrical, plumbing systems. Typically when we're doing LCAs right now, we're just looking at the structure and envelope, maybe some of the interiors, but there's definitely a lot of interest in looking at the MEP systems as well, mechanical, electrical, plumbing. And those emissions can be quite significant too. So there are many blind spots in a way. There's still a lot of like scopes that we need to include as we expand this analysis, but that would be something that also would eventually factor its way into kind of a retrofit type of a calculation.
Awesome. And cheers to you for you're getting a lot of very technical questions and you're answering them very well on the fly. So I've got another one for you. So we'll keep them coming. Sure. Can you give us a quick overview of the current thinking and the state of assessment practice around how using wood in buildings can act as a carbon sink?
That will be a longer question. There's different approaches to doing this. Maybe I'll just send a link to, like, I did an 1.5-hour presentation on this, like diving deep into biogenic carbon and this current state of the art. I would say there's not a lot of consensus per se right now. There's a lot of complexities in this conversation. Forests are an extremely dynamic system, and it's sometimes hard to just put a number to it per se. But how do I say it? I think there's some studies that are probably overstating the benefits in a way. If you just take the total carbon in the building and you multiply it by -1, and then you're saying it's like a negative emission building, there's a lot of this depends on how the forest is managed, and there's a dynamic component to this as to like when these emissions happen over time. Like LCA is kind of a static analysis, but where the leading edge is looking at more of dynamic analysis around biogenic carbon. So like, when is this carbon actually getting sucked in the forest? And also, how long are you storing that carbon in the building? And what's the benefit of that versus something like burning it for bioenergy? Like, there's differences in climate benefit from a time dynamic perspective. And anyways, I'm probably not providing a clear answer right now, but it's I'm also trying to wrap my head around what's the best approach around this right now.
Yeah, I think if there's any way to link that presentation, there'd probably be some interested people in the audience.
Yeah.
Awesome. And while you're searching, I'll have you multitask. I've got another question here also about sequestering carbon. So what about specifying processes? Like, can we specify processes that sequester carbon, such as, I'm not sure if you're familiar with this one, but one used by the Canadian company Carbon Cure. So Jim says the strength is improved, allowing lower amounts and thereby lowering costs as well. So I don't know if you're familiar with this technology or if you know of any other
Carbon Cure. Sorry, I may have missed the first part, but the Carbon Cure, I'm definitely aware of. So I would just say that, like, my understanding of their current technology is that I don't think their reductions are actually that significant at this stage. Like, the percentages that I've heard from people is more in the 1 to 5% reduction per meter cubed of concrete, which is not that significant. There's a lot of things you can do to concrete. Like I already showed you could get to 40% or even 50% reductions, right? So I think it's a good approach to like explore all the avenues of how you can actually, sequester carbon and whatnot. I think there's a lot of value to it, but I would just encourage you to actually look into the numbers and see like what is the actual reductions that are being achieved from this, and how does this compare to even conventional strategies. I'm all for exploring the full range of things, but I think they get a lot of attention. Yeah.
Awesome. Yeah, it's always good to look at the data below the headlines sometimes. Yeah. So a question here from Matthew: what are the potential liabilities, difficulties, and long-term side effects of using higher SCM content in construction, And second part to the question, are there firmly established standards for SCM content that avoid these pitfalls and which could be adopted into codes?
So my understanding is that there's not like that much of a risk in a way of including these SCMs, but I have also heard that concern raised before. And I don't have like I haven't looked deep into like, the health impacts or whatnot, but my understanding is that like once it's in the concrete, it's pretty stable and it's been widely used for already, and it's already common part for many projects. So, but I don't think I can comment specifically on that. Maybe there's other people that have more looked into this more in depth than I have.
Yeah, no worries there. So another question on materials. Have you seen an increase in the usage of plant-based rigid foam in your own experience?
In my own experience, not yet. I mean, no, I haven't seen it yet, but I think there's I think the embodied carbon conversation will definitely push for that. And hopefully it makes its way into more and more projects. I will say there's a difference between, for example, using wood and other agricultural residues, for example, to create insulation products, for example. I think those products that have more of a kind of a faster growth cycle, there's a very different equation for quantifying the biogenic carbon storage around that and the benefit associated with that versus something like a tree that might take like 60 years to go through a rotation or 40 years or whatnot, right? And so there's a lot more, I think it's much more clear around those like faster growing, like hemp, straw bale, etc., versus wood.
Perfect. Yeah, and really related to what you just said, would you recommend natural alternatives for thermal insulation? So for example, cellulose, wood fiber, hemp fiber, and etc.
Yes.
Awesome. I like the easy answers. Perfect. Okay. And a question here from Angela. The City of Ottawa is drafting our green standard. It'll be a step approach like the BC code. The current draft does not include embodied carbon. What would be your recommendations for a robust approach to embodied carbon in a green standard?
So first, like requiring disclosure, I think that's an important one. You could potentially, like, if you want a more simplified approach, maybe even just piggyback off of like, I don't know if LEED is part of that already, but like you could specify, for example, like you need to get that credit in LEED, the MRC1 credit, which is, and when then kind of rely on them in a way because within that LEED credit, you get 1 point for just disclosure, 2 points for 5% reduction, 3 points for a 10% reduction, 4 points for 20% reduction. So like something like that, you can kind of like maybe just point to that. I would say that so I'm working with the City of Vancouver on developing embodied carbon modeling guidelines. We're soon going to be getting a lot of external feedback from the industry around this topic, but I think we need a lot better guidance on some of these things, like how do you define baselines, how do you and from which you define reductions from, et cetera. And so hopefully soon there will be more resources that you can kind of point to or build off of, but I recognize right now it can be a bit of a challenge. That said, there's also, what's it called? embodiedcarbonpolicies.com. There was like a big report that looked at 52 different embodied carbon policies and looked at best practices around the world. So I would encourage policymakers to look at that document. That's to kind of get some different approaches, but definitely I think in BC, we obviously have like what the City of Vancouver has done on that. And I think the City of Vancouver is doing a lot of good thinking around how to craft that policy, and there's more to come on that.
Awesome. Yeah, it's always better when we don't have to have every single jurisdiction trying to reinvent it and start from scratch.
And right now there's a lot of experimentation happening, and I think that's also good, but because I don't want to be like, okay, whatever Vancouver's doing is like, this is the last word on it, right? Like, I think we need a lot of experimentation on different approaches, and we'll all learn from each other.
Awesome. Yeah, and I do see some sharing in the chat too, which is great. If anyone else has resources to share in this, always feel free to keep that conversation going. It's awesome to see. And question here, how does the embodied carbon in a residential wood frame building compare to the sequestered carbon in the wood? I understand it depends on how the forests are managed. Can we get an estimate for Vancouver? So this might be another data, source specific and lots of data that goes into it, but wondering if you have any answers there for that one.
So I think the more conservative way of estimating this is to not account for the carbon sequestered in the wood per se. And if you just look at which would basically mean we're really just accounting for the fossil fuel related emissions with like extracting the wood and manufacturing, processing, et cetera, right? And so, but yeah, low rise wood framed constructions are generally in the, let's say 100 to 200 kilograms of CO2 per meter squared range. Obviously, it can range quite a bit. Actually, Chris Magwood did a great study with NRCan. So I'd encourage you to look at that project. And actually, I think with that report. And then key thing to note about their methodology is that they do account for that biogenic carbon storage. So that's already baked into their numbers. So they have like, they can get negative numbers with how they've done that methodology. But if you're interested in how that shakes out for the low rise residential, that'll be a good report to look at.
Awesome. And we're just coming up on 12:45 here. So I'm just going to give you one more question, but there are a lot more here in the Q&A box. Can folks reach out to you if they want to keep this conversation going?
You're welcome to reach out. I will just say I may be a little bit slow to respond. I have a lot going on right now. But yes, I will try to answer your question if yes.
All good, all good. So our last question for you today then is, how do we update embodied carbon information rapidly enough to take into account changes in industrial processes so that we can reward those changes?
So I would say looking at EPDs, so environmental product declarations. So there's the EC3 database, if you're not familiar, just search up EC3 from buildingtransparency.org. They have created kind of an open source database of like thousands of product data points. And that's going to be a constantly updating thing. So you're always going to, and manufacturers have to update their EPDs every 5 years. And so that's going to be a great source of information. You can kind of figure out within each category, what's the range, how they compare, what's available locally, et cetera. And I think we need to have a much bigger push in Canada for our manufacturers to produce data points on that. We're already starting to see some local ready mix suppliers produce some EPDs for specific concrete mixes that they produce. So yeah, I think that's how that would be integrated. And then that could then feed into whole building LCA modeling.
Awesome. Thank you so much. These are some really heavy questions, and it was awesome to see you just swinging them out of the park. And thank you everybody for joining today. I think this just shows how much the sector is excited to take on this conversation and keep learning. So thank you so much, Anthony. Thank you, everybody. And with that, I will send you off to enjoy the rest of your Friday.
Thanks, everyone.
Take care.
Cheers.